In the last video, we looked at the first of our three fun with flags. Oh, sorry, that was a Big Bang Theory reference. First of three of my favorite differential equations. That was Matthew's equation for stability of a oscillating pendulum, forced pendulum. So in this video, we're going to look at the Duffing equation with damping and forcing. So here's the equation. It is a second order ordinary differential equation. Second order term, first order term. The first order term corresponds to damping, comes from the damping. And then you'll notice there's this alpha u cubed term, so that's what makes it nonlinear because of the u cubed. And then there's forcing on the right hand side with a forcing amplitude f and a forcing frequency cap omega. So there's a lot of different things that you can vary in this equation in order to see what the effect is. Essentially, you can think of this as a pendulum with a spring. No, sorry, not a pendulum, but a spring mass system. This is going to be a very lousy picture, I apologize. So you have a mass M, and you have a damper, like so. And then there's forcing, so this gets forced with this F cosine cap omega t. So this spring is now nonlinear. So normally you have a linear spring, and if you have a linear spring, you just have this u term here. Because of the nonlinearity, we're going to have u plus alpha u cubed. And so the bigger alpha gets, the more nonlinear the spring becomes. So you have the mass going back and forth. There's damping, which is given by D. Oh, that's a terrible looking damper. Sorry about that, folks. And then again, this forcing acting on the mass itself. So spring, mass, damper with forcing. And then we can turn on and off anything we want. So if you just want a regular linear spring with no damping, you can set D is equal to 0 to get rid of that term. Nonlinearity, alpha is equal to 0 to get rid of that term. No forcing. And then you just have a regular harmonic oscillator that goes back and forth just like the pendulum that we discussed in the last video. Or you can turn on damping, turn on forcing, turn on nonlinearity. So we can turn on and off these various effects as we look at it. So let's try that. So let's first look at D is 0, no damping, no nonlinearity, and no forcing. So this is just a regular spring wobbling back and forth. So on the left, this is what you'll see in all these plots. We have a plot of u versus time. So time is like this. And then on the right is what's called a phase plane plot. So this is a plot of u versus u dot. So the position versus velocity of the mass. So you see the mass is going back and forth. This is its neutral position. It's going back and forth, left, right, left, right, left, right, on and on and on, but it maintains the same amplitude. And so in the phase plane, that looks like just a circle. That's called a limit cycle solution. So there's one solution that repeats over and over and over again. And the phase plane tells you that. So same amplitude, same frequency, and you see that as a closed circle for a limit cycle solution in the phase plane. Now if you add in a little bit of damping, so still no forcing and no nonlinearity, you just have your spring and now you damp it. So as you'd expect, over time, the amplitude of the oscillation will decrease, and this is a long time period. This goes to 150 in time here. In the phase plane plot, it starts here at t is equal to 0, and it traces out this spiraling trajectory in towards the origin as the damping takes effect. Now let's get things a little bit more interesting. So now let's turn off the damping, so no damping, still no nonlinearity, and just look at a small amount of forcing. So it's just small, it's 0.1, but we're going to force at the natural frequency of this system. So it's a spring mass system. It has a natural frequency based on the spring and the mass characteristics. and the natural frequency corresponds to kappa omega is equal to 1, and we're going to force it at that frequency. Small amount of forcing, but nevertheless we're going to force it at the natural frequency. And so what you see is resonance. So the amplitude grows continuously with time. Now we're starting here and spiraling out in the phase plane as the trajectory proceeds in time. So that's resonance caused by a forcing at the natural frequency. Now let's look at a case now with small amount of nonlinearity. So we have the same parameters as in the previous slide. So with the resonance occurring because we're forcing at the natural frequency, but we're just going to add in a small amount of nonlinearity. So alpha is 0.1. Everything else is the same. So instead of the growing amplitude, what you'll see is this modulating oscillation. So essentially what's happened is the nonlinearity, even though it's not much nonlinearity, that nonlinearity has broken the resonance. So it's mitigated the resonance, and that's all it takes, is to just throw the system off by a little bit. It gets rid of the resonance and then therefore introduces this modulation in the amplitude. And you can see how that effect shows up in the phase plane. So nothing ever gets bigger than this about 1.6 or 7 or so here. And so you have a prescribed maximum magnitude, and then it goes back and forth between these, in and out, in and out, in and out. Okay, now let's get even more interesting. So this system does exhibit chaotic behavior, and chaos, the way we think about it, the way we use it in normal English intercourse, is we think of it as something that's random, that it's unpredictable. In fact, that's not what it means at all. So chaos is really called deterministic chaos. And the deterministic part is important because deterministic means we know the governing equation. The equation determines the behavior of the system. It captures all of the seeming random behavior that is exhibited by the system. So it is deterministic. So it looks chaotic, but it's actually a deterministic chaos. And so I want to illustrate some of the features of that through this force Duffing equation. So we have the nonlinearity, as we've mentioned. We have the damping. We have the forcing. And what I'm going to do is I'm going to keep all of these parameters the same. So the damping is small. It's only 0.1. Alpha is 5. So that's the nonlinearity, which is relatively large. And then the frequency of the forcing is going to be 1.4. You'll notice that is not at the natural frequency of 1. So we're not forcing at the natural frequency. So anything you see is not because of that. And then the only thing we're going to change is F, the forcing amplitude. Everything else, damping, nonlinearity, and forcing frequency will be the same. And we're just going to increase the forcing amplitude and see how the force Duffing equation responds to that. So here is a relatively small forcing, 0.1, and you'll see there's some seemingly a little strange behavior at the beginning. That's what I call here an initial transient. You'll notice after some period of time, that initial transient essentially goes away, and we have our regular oscillation that we had before. So if you don't plot the first part, the initial transient, and just plot after a certain period of time, you essentially get a limit cycle solution as we had before. So again, this is with nonlinearity, with some forcing, and with damping, but they're all just the right balance. So after these initial transients, you get this limit cycle type of behavior. So it looks linear. It looks very similar to the linear oscillator that we had in the very first case. Now, as we increase F, things are going to get really messy really fast. So we're going to introduce another way of looking at the behavior of the solution in these systems. So we have the plot of U versus T, which I've been showing you, and we have the phase plane plot, which is the velocity relative to the position. And so we're going to introduce this Poincare section, which is built off of the phase plane plot. So the phase plane plot shows you the entire trajectory for all time of a system. And as you'll see, those can get I will show them to you. They get really, really messy. So to kind of make some sense of the behavior of the system, what the Poincare section does is, and it's named after Henri Poincare from the late 1800s. So what it does is it's basically like a strobe light. Of course, you guys don't know what a strobe light is because you weren't alive in the 1970s. But a strobe light, it just takes a picture at a predefined frequency. So essentially the way you can think of it as the trajectory of the solution is proceeding in the phase plane, and it'll get increasingly messy looking. But what we're going to do is just take a snapshot every integer increment of a prescribed frequency. Where is the solution? So rather than having a continuous curve trajectory, we're going to have a series of dots. And those dots will give us some sense for the types of behaviors that are arising in these systems. So they're going to be done, so the strobe light frequency is going to be relative to the forcing frequency. There's two frequencies in this problem. There's the natural frequency of oscillation, which is 1, and then there is the forcing frequency, which is which is this 1.4 that we have back here. So that's 1.4. So we're going to use integer multiples of 1.4, take a strobe light snapshot of the system in terms of the phase plane, and then as you'll see, that'll produce a series of dots, which will be characteristic of the solution. We'll explain it as we go. So we're going to increase the forcing amplitude, and then we're going to see how the system behaves in terms of all three plots. I'll show one or two examples of all three, and then we'll look at the Poincare section later on. Okay, so here is so I already plotted this, so I won't plot it again. So here is U versus time, and the phase plane plot for the case with f is 0.1. So again, it looks like a limit cycle solution. So when you just take a strobe light picture at the frequency of the forcing, every time you look, where is the trajectory? It's always going to be at the same point. So it hits this point, goes around, hits this point again, goes around, hits this point again. So for a limit cycle solution, the Poincare section is simply a single point. If we increase to f is equal to 10, so it was 0.1, now it's 10, so by 2 orders of magnitude, you can see that the u versus t behavior is getting a little more complicated. However, again, after some initial transient, if you don't include that, and you just plot the phase plane plot for times after we take out the initial transient, you still get a very regular looking behavior. So there's actually two lobes then in, I did a terrible job there, but there's two separate lobes, and it just keeps going back and forth between them. So essentially what we have now are two distinct periods, or two distinct loops within which the solution is traversing. So the way that looks in the Poincare section is as two dots. So if you have one limit cycle, you get one dot. If you have two limit cycles, then you get two dots. Okay, well, that's not terribly exciting, but watch what happens as we continue to increase it. So increase it again, another order of magnitude, f is equal to 10. You can see now the oscillation is very messy. There's all kinds of frequencies going on in there. The phase plane plot is a complete mess, just looks like a dropped spaghetti on the floor, and really can't make any heads or tails of what's going on there in terms of the behavior of the solution. All right, so then we can turn to the Poincare section, and you get this. And you say, whoa, wait a second. That looks very different than what we had before. And you're right. Each one of these dots that you see, each of those single dots is when the solution came around and the strobe light hit, that's where the trajectory was. So each dot in this plot shows at a particular time where the u and the u dot, the position and the velocity were, as you can think of it as it came through the plane. Now the first thing you notice is it's kind of cool looking. It's quite pretty actually. But the other thing you notice is it clearly has a very particular structure to it. So it's clearly more than just the two limit cycle frequencies that we had in the previous case. This is chaos, but it has a very particular structure to it. You can see that it does not fill up the entire phase plane. It's confined to a specific region of the phase plane. We call that the strange attractor. So an attractor is the region in the phase plane where the solution resides. A strange attractor has some of the properties that I'm going to illustrate in the next few slides. But not only is it contained within this particular region, the strange attractor, it has particular structure within it. There's whole regions of the domain of the phase plane where it never hits. And if you just keep letting this go longer and longer and longer for many, many, many time units, it'll just keep filling in the same regions that we already have. These regions and these regions outside will never have any dots. So it has this very specific structure. It's very unique, but again, it's deterministic, and everything is just going to keep falling back on not the exact same points, but it's just going to fill in more points on some of these curves. So let's take a look at this region right here. So let's blow this up. I just picked one region of the strange attractor in the phase plane, of the Poincare section of the phase plane, and let's just blow it up and see what it looks like. So it's the same information, the same data, but it just blown up. So this is now a small region in U and in U dot. And the first thing you'll notice is it kind of looks the same. I mean, it's just, I can't really tell the scale. There's no obvious way to, when I look at this, to say that, oh, well, I zoomed in by 100% or 1,000%. It's still just a bunch of dots with a very specific structure to it, and you see these interesting shapes and so on. And again, as you do more, as you let this go on longer, you're just going to get more dots along these same kind of striations in the phase plane. So we call that a fractal, which I'll mention on the next slide, but we call it a fractal. If we zoom in again, so now I'm going to zoom in on this region right here, and it looks like this. So once again, there's no way for me to tell just by looking at it. If I just look at these two figures, obviously this one is the overall one because I can see the complete strange attractor. But between these two, there's no way to tell which one is a subset of the other than the fact that I've included the scales on here. But just looking at the figure, looking at the Poincare section, there's no way to tell. So this is called a fractal, where when you look at a system in terms of the phase plane or whatever it is, you look at it on different scales and it appears the same, it looks the same. You see the same structures, you see the same behavior on all these different scales. So that's called a fractal. Not every chaotic system has this fractal behavior, but many of them do. And you can look online. There's many, many beautiful Mandelbrot sets and Julian sets and so forth. There's all kinds of interesting examples of fractals. Some of them are quite beautiful looking. Now, there's still more in this system. There's still more information that we can extract out of these solutions. Each one of these is just solving a differential equation from t is equal to 0 with a set of initial conditions and solving in time. There's nothing fundamentally different about each of these solutions in terms of how we get them numerically. What's different is how the solutions themselves behave and the characteristics that they display. So we're going to introduce one more way of looking at this through what's called a bifurcation diagram. And it's going to help us understand what's going on and why this one is so much more complicated than this one. And what's happened between, first of all, what's happened between here and here, and what's happened between here and here. That's really what we want to know. Okay, so let's look at a bifurcation, talk about what a bifurcation diagram is, and then we'll take a look at it for the force Duffing equation. So a bifurcation point is a set of values that when you cross a particular critical value, you have a different type of solution. So it might be that for alpha less than well, let's talk about f. So for f less than a certain value, it's stable. For f beyond a certain value, it's unstable. So that value, the critical value of f, we call that a bifurcation point. It could be a point where we go from one limit cycle to two limit cycles, or from two limit cycles to four, or however the solution changes. So a bifurcation point is a point where the solution, it's a value of the parameter where the solution changes in some qualitative way, not just quantitatively, not just a little bit more, a little bit less, but there's a qualitative change in the solution. So let's take a look at the bifurcation diagram for the force Duffing equation. Now this corresponds to actually thousands of solutions of the force Duffing equation. So before we were looking at one solution at a time. This bifurcation plot represents thousands of solutions. Each one of these dots is actually a solution of the force Duffing equation. This is F, so starting with 60 up to 150, so this is increasing the forcing amplitude, and this is U, and it's a measure of something about the system, all right, which is all I really need to say. So for example, you'll notice here, we'll zoom in on this in the next slide, but look at this region right here. So right here, for this particular value of f, say 120, you'll notice that it looks like there's only two solutions. There's actually more. There's actually two lines here, not just one. But it looks like there's just a small number of solutions. So either the solution is here or it's here. When we get to this region here, all of a sudden it looks like there's many solutions. I don't know, is that thousands of solutions? Is that infinity of solutions? And then there's a region in here where it seems to kind of clean up, and there's, again, a small finite number of solutions, and it seems to go chaotic again. And that's exactly what's happening. So we'll talk about this region right here, what's happening, and then what's happening right here, and also we'll come back in a few slides, we'll talk about this down here, which is kind of remarkable. Okay, so let's zoom in on this portion of the bifurcation diagram. Again, each one of these dots represents a single solution of the force Duffing equation. So now you can a little more clearly see there's actually two here, two different solutions, and they bifurcate. So this is a bifurcation point right here, where this one solution bifurcates into two, and this one solution bifurcates into two. So we go from 2 to 4 periods. Then again, there's another one here. So this one splits into 2, this one splits into 2, a little harder to see, this one splits into 2, and so forth. So that's called period doubling, and period doubling is one route to chaos. There's various routes to chaos, how a solution goes from non-chaotic to chaotic, and period doubling is one of those routes. That's what's happening here. And so the period doubles, keeps doubling until all of a sudden you have chaos. But notice what happens after. There's some range of f where you have chaos, but then there's this narrow range of f in here where it all of a sudden magically seems to kind of clean itself up. And now we go back to having a finite number of solutions. And then it goes through another set of period doublings, which you can't see, it's too small to see on this plot, and then it goes chaotic again. It's really very unusual, strange. So, and again, this is as you increase f. So as you increase f, it's getting period doubling, so more and more limit cycles. All of a sudden it's chaotic with a strange attractor like I showed previously, and then all of a sudden it becomes much more cleaned up again, and then it goes back to being chaotic. And then finally, look at this. So we go from chaos for this value of f to increase f just slightly, and look what happens. It goes back to one single solution at about 148. F is 148. So for 147, chaos. For 149, there's one single solution, one limit cycle solution. So that's the nature of chaos. And in order for you to have chaos, you have to have nonlinearity. Not all linear systems exhibit chaos, but in order to have chaos, you do have to have a nonlinear system, which is what we have here. All right, let's see what else we want to say here. So we have a number of these different types of bifurcations between limit cycles and chaotic. If you just keep increasing F, you get this over and over again, kind of transitions and bifurcations. It's really, really interesting. So the way we normally think of plotting dependent variables as functions of their independent variables, in this case time. So that's one way to look at the solution. Another way is through a phase plane plot, which is velocity versus position, traces out a trajectory in the phase plane. And then another way is to take strobe light snapshots of your phase plane to get a Poincare section. And then a fourth way is to look at bifurcation diagrams, where you can see the values of your parameters, in this case F, at which the fundamental character of the solution changes, bifurcates. In this case, we have this period doubling. Again, that's just one route to chaos, and each route to chaos has a different signature in these plots: phase plane, Poincare, and bifurcation diagrams. Okay, in the next video we'll look at one of my favorite nonlinear systems, the Saltzman-Lorenz model.